Okay, so this is lesson 3-7, translating graphs of absolute value functions. So I'll give you a second to write that down because we're not looking at linear functions anymore, just functions. Okay, so now this first one, go ahead and draw this graph. And I would write this. This is your parent function, that original function. F of x equals the absolute value of x. So this is what we will start with on every one. The reason it works like this, absolute value. If we take the absolute value of 2, that would be 2. If we take the absolute value of -2, that's still 2. So we have two of the same outputs for different inputs. So that's why it kind of does the same thing, just the opposite direction. So go ahead and draw that, and then we will look at an example. The reason this works is you plug numbers in for x. So like I just said, the 2 and -2. So when we plugged in +2, we got an answer of 2. That's a point. When we plugged in -2, we still got 2. That's another point. That's how we can see. And you would just keep plugging in numbers until you find the vertex, which is the point where it changes direction. Okay, so looking at example 1, we have an A and a B. It says graph g of x equals the absolute value of x plus k, and g of x equals the absolute value of x minus h. Or that's what we're doing. So if those letters confuse you, just calm down, wait till we get to some numbers. So graph each function and compare it to the original parent function. Okay, and then describe your domain and range. Domain is your x value, range is your y. Okay, so on problem A, here we go with some actual numbers. It says g of x equals the absolute value of x plus 3. Okay, so absolute value of x is our parent function, the original one. So the only thing different is we're adding 3. We know when we're adding or subtracting that it is a translation. Okay, and we're adding outside of that original function, so that means it's a vertical translation, and we can use our definitions to help us from the last lesson. We're still talking about that stuff. So this is going to be a vertical translation. Okay, that's how we can compare it. Now to graph it, you just make a table. Okay, so they use -2, -1, 0, 1, and 2 for their input values, their x. That's typically the numbers I start with, just because you kind of get some negatives and positives. But you choose these values. Okay, so they choose those values, then you're literally just plugging them in for x and solving for y. So when we plug -2 in there, the absolute value of -2 is +2, plus 3 is 5. That's where we get this 5. So then we plug in -1. The absolute value of -1 is 1, plus 3 is 4. That's where we get this 4. Then when we plug in 0, that just is 0. So then we get 3. We plug in 1, we get 4, 2, 5. So if you notice, our vertex, or the point where it changes direction, is at 0, 3. So we could graph those. So right here they have, this is, black one is that parent function, the original one. So we have several points that we can graph. -2, 5, -1, 4, 0, 3, 1, 4, and 2, 5. And since we said it was a vertical translation, we should be able to just slide it up 3. 1, 2, 3. And that's exactly what happened. So now for the domain and range. It's much easier than it sounds. So for your domain, that's your x values. You look at this graph. And if you notice, it goes this way. This arrow means it continues on and on forever. And it goes this way. This arrow shows that it goes on and on forever. This is the x-axis. So if it goes on and on forever this way and this way, your x value or your domain would be all real numbers. Okay, for the range, that's your y-axis. Let me change colors. So we're looking this way. Well, it starts right here. That's at 1, 2, 3 on the y-axis, and then it goes up both ways forever. So it's not anywhere below that, but it goes on and on forever above that. So for your range, you would say that y is greater than or equal to 3. And that's it. Okay, so now we're going to look at another one. We'll look at B. This says m of x equals the absolute value of x minus 2. So again, we're adding or subtracting, so that tells us it's a translation. and we are doing it inside the function, which tells us it's horizontal. So we know we have a horizontal translation, which means it's going to slide left or right from the original function. Okay, so then we make a table to plug in some x values. Now, if you notice on this one, they didn't plug in any negatives. They just started, but it's because they knew where the vertex was. Just start with these. You just might have to extend your table one direction or the other until you figure out where that vertex is. Okay, so they plugged in these numbers. So if I plug in 0 minus 2 is negative 2, but the absolute value of that is positive 2. 1 minus 2 is negative 1. Absolute value of that is 1. When you plug in 2, 2 minus 2 is 0. 3 minus 2 is 1. And 4 minus 2 is 2. So there's our vertex. Let me slide down a little and erase this. Okay, so here's our graph over here. The black one is the original parent function, and the blue is the new one. So they just graphed these points, 0, 2, 1, 1, 2, 0, 3, 1, and 4, 2. And you can go on. So I've done it before where I ended up having like 3 numbers on this side, but only 1 on this side. It's still going to continue even if you don't have the points there. Okay, so now that we've graphed it, we can state our domain and range. Our domain is our x values, and it goes on and on forever the negative way and on forever the positive way. So our domain is all real numbers again. Oftentimes, that's what it is, a lot. So then our range, which is our y values. So looking at your y-axis, it's at 0, and then it goes up from there. So your range would be y is greater than or equal to 0. Okay, so I want you to attempt 1 and 2. If you can't, you can continue on and watch me do it, but I want you to try it, and then you can watch me go over it. Okay, on 1 and 2, we are graphing and comparing to the original function. I don't know if you can see that, but that says f of x equals the absolute value of x, our parent function. So we've got to graph it, compare it, and then state our domain and our range. So on number 1, I have h of x equals the absolute value of x minus 1. Since I am adding or subtracting outside of the function, okay, that means, okay, I'm not sure what the thing is doing. Hold on. Let me switch that a little better. I don't know where it was going. Maybe it'll stay now. Okay, so since we have minus 1 outside of the function, that means this is a vertical translation. So I already can compare it. Okay, and we can make a table to find some of our values. I'm just going to have to hold this. All right, so for x and y, we're just going to plug in some numbers. I'm just going to make it easy. We just have to find where the vertex is. So when I plug those in, the absolute value of negative 2 is positive 2. Then 2 minus 1 is 1. Negative 1, absolute value of that is 1. Minus 1 is 0. Plug in 0, you're left with negative 1. 1, absolute value of that is 1. Minus 1 is 0. And then absolute value of 2 is 2. Minus 1 is 1. So our vertex is right there. Okay, so whenever I graph that, I have negative 2, 1, negative 1, 0, 0, negative 1, 1, 0, 2, 1. Okay, we can double check a vertical translation. It translated down. So it went down 1 unit. We don't necessarily have to put that. I just wanted to. So that one was h of x. Now for your domain and range, you just look. Domain is your x. If you look at this x-axis, it goes all the way that way, never ending, and all the way that way. So my domain is all real numbers. Your range is your y. If you look at your y-axis, the lowest it goes is right here. And then it goes up from there. So y has to be greater than or equal to negative 1. That's your domain and your range. Okay, what I'm going to do for problem number 2, I'm just going to graph it on this same one. If you do them separate, that's okay. I'm still just looking at the green one now, but I will switch colors so it doesn't confuse you. Okay, on number 2, we have absolute value of x plus 4. So again, I'm adding or subtracting, but this time it's inside the function, so that is a horizontal translation. Okay, so now I'll make a table. These are just my go-to numbers. Okay, it doesn't matter what numbers you use. Sometimes we'll get into later on, you've got to try and figure out where the vertex is, where it comes to a point and turns around, and sometimes you have to end up going further one way or another to figure out where that is. Okay, so -2. -2 plus 4 is 2. The absolute value of that is 2. -1 plus 4 is 3. Absolute value of 3 is 3. 0 plus 4 is 4. 1 plus 4 is 5. 2 plus 4 is 6. So, I don't know where my vertex is. So, I'm just going to extend it a little further both ways. Let's see, I'll plug in. If it doesn't work this way, we'll just extend it the other way. All I'm doing is going further on my table. I just ran out of room. So, -3 plus 4 is 1. -4 plus 4 is 0. It just still keeps going. -5 plus 4 is -1. Absolute value of that is 1. I finally found it. So my vertex is right here. So on this one, I'm going to go and do my vertex first. So 1, 2, 3, 4. -4 is 0. -5, 1. -3, 1. So it's further over here. That is n of x. So from the green one to that one, we had a horizontal translation, okay, and it went left 4 units. Wait, did I do that right? Hold on, -4, 0. 1, 2, 3. Oh, sorry, y'all. My graph should have been right there. I knew that looked funny, because it translated 4 units left. Okay, since it's plus 4, think of it as that goes negative. If it had been -4, it would move on the positive side. I know that's kind of weird, but that's what it does. So 4 units left. Okay, so for domain and range, domain is our x. If I look over here, it's all of our x's, so all real numbers. And our range on the y-axis is at 0 and everything above. So y is greater than or equal to 0. Moving on to example 2. So this one says graph each function, compare it to the parent function, and describe the domain and range again. So on A, I have that q of x equals 2 times the absolute value of x. So from this parent function to this, we just have times 2. Since it's being multiplied, we know that it is a stretch or a shrink. It's outside the function, so we know it's vertical, and it's a whole number, so we know it is a vertical stretch, okay? And I know that from those definitions we wrote. You're going to need to use that on this lesson too, from 3.6. Okay, so now, when we graph it, let's just make a table, again, like in the previous example. We just plug numbers in for x, our domain. So then, whenever I plug that into this equation, so -2. Well, the absolute value of -2 is positive 2. 2 times 2 is 4. That's how we get this. This is your y. Okay, if I plug in -1, the absolute value of -1 is 1. Times 2 is 2. Well, 0 times anything is 0. 1 times 2 is 2, and 2 times 2 is 4. So we have our points. Now we can graph them. This black one is just the parent function. You can make another table for that too. You're just plugging in right here. So then the blue one is our new equation. So -2, 4, -1, 2, 0, 0, 1, 2, and 2, 4. There is our new function. So hold on, let me get off of that. Okay, now on to B, and this one's a little frustrating because you can't see the problem. So we are looking up here at B now. So we have times negative half. It's being multiplied, so we know it is a stretch or a shrink. It's outside the function, so we know it's vertical. And it's a fraction, so we know it's a vertical shrink. Also, we have a negative outside the function, so that tells us it's going to reflect, okay, excuse me, across the x-axis. So, lost my place again. Okay, so right here, we make a table with some x values, and we just plug them into that equation. So I'm going to use this one down here since I can't see it at the top. So plugging in negative 2, the absolute value of negative 2 is positive 2, times negative 1/2, the 2's actually cancel, so that's negative 1. If I plug in negative 1, the absolute value of negative 1 is positive 1, times negative 1/2 is negative 1/2. If we plug in 0, we just get 0, 1 we get negative 1/2, and 2, negative 1. So then we graph those. So negative 2, negative 1, negative 1, negative 1/2, 0, 0, 1, negative 1/2, and 2, negative 1/2. So if you notice, it stretched, and it flipped because of that reflection. We had two things happen on that one. Okay, so what I want you to do, let's see, this was example 2. You're going to try these two, all right? If you just absolutely cannot figure it out, you can press play and go over it with me. But I would like you to try these on your own. So you're going to tell me what it is, like vertical shrink, like on the first one we did. Graph it, so you got to make a table so that you can graph it. Okay, and then describe the domain and range. Oops, I forgot I didn't do that. So back up here, sorry y'all. On this first one, your x values, looking at your x-axis, it goes on and on forever the negative way, and it goes on and on forever the positive way. So our domain would be all real numbers. And for your range, well, if you notice, that's the y-axis. Everything is above this point. So our range is that y is greater than or equal to 0. Okay, then on B, switch colors. My domain, again, my x values, it's still going on both ways, so your domain is still all real numbers. And like I told y'all, on almost all of these, your domain is. The range is everything below 0. So now instead of greater than or equal to, it's less than or equal to 0. Okay, so back down to the problems you're going to try, 3 and 4. You're going to also then have to tell me your domain and range by looking at your graph. So pause the video, try that, and I'll go over it. Okay, on 3 and 4, we're doing the same thing, but we're just having to use all of our options. So I went ahead and I still have my parent function graphed. F of x equals the absolute value of x. So on 3, we have that t of x equals negative 3 times the absolute value of x. So right off the bat, we use our definitions and work on those to see that since it is outside the function and it's being multiplied, we know it is either a vertical stretch or a vertical shrink. Okay, so then we look at it's a whole number. That tells us, gotta double check myself, I get confused on these some too, that is a vertical stretch. When it's a whole number outside and it's being multiplied, it's a vertical stretch. We can tell that before we even graph it. Okay, so then to graph it, we make a table and plug in some numbers. So if I have a negative 2 in here, the absolute value of negative 2 is positive 2. Positive 2 times negative 3 is negative 6. And to plug in negative 1, that would be 1 times negative 3 is negative 3. Plug in 0, get 0. Plug in 1, 1 times negative 3, and 2 times negative 3 is negative 6. Okay, so if I graph that, my vertex is at 0, 0 again, same one, which it should be. Since it's a vertical shrink or stretch, it should start at the same vertex, and it just kind of does that. Either go in or go out. So my next point's negative 1, negative 3. Oh, yeah, sorry. -2, -6. I forgot it also flipped. Do you remember why? Because it's a negative. That shows us it was a reflection also. So then we have 1, -3, 2, -6. So it got skinnier. It was a shrink. Okay, it got skinnier, but it also flipped because of the negative. So this is t of x. Okay, on number 4, I'm just going to do it on the same graph again since they both start out with the green one, f of x equals absolute value of x. So on this one, again, it's outside the function and it's being multiplied, so we know it's a vertical shrink or a stretch. Since it is a fraction, that is a vertical, did I say that right? This one is a vertical shrink. Oh, I know what I was thinking. I said it got smaller, so that was a shrink. That was a stretch because what they've done is they've stretched the points out further, which then made it come in more. I'm sorry if I confused you when I said that a while ago. Okay, so on a vertical shrink. Now let's go ahead and plug in some numbers. So if I plug in -2, absolute value of -2 is 2 times 1/4 is 1/2. Okay, -1, that'd be 1, that'd be 1/4, 0, 0, 1/4, 1/2. Excuse me. So on this one, even though it's a shrink, it's because we're shrinking those points even closer together. We're getting, in this case, fractions. So 0, 0 is still my vertex. I have -1, 1/4. Well, we know 1/2 is there. 1/4 is half of half. So it's like, boop, right there. -2, 1/2. 1, 1/4, 2, 1/2. And if we went further, if I plugged in 3, I would probably get 3/4. So this one is super wide. So V of x. That is a vertical shrink. So even though it looks like it stretched, it's a shrink because we've shrunk the points down. Okay, and the stretch, it looks skinnier, like we shrunk it, because we stretched out our points. Okay, next what we're going to look at is we just have a little bit more complex equation or function. So it says graph f of x equals the absolute value of x plus 2 minus 3. That's our parent function. And g of x equals the absolute value of 2x plus 2 minus 3. Compare the graph of g to the graph of f. So if you look at f of x, we have x plus 2 and then minus 3. Over here we have 2x plus 2 minus 3. So the only difference, let me switch colors, is where we have x here, we have a 2x over here. Since that's the only difference, that means g of x is really just f of 2x, which means everywhere that we had an x in f of x, we just rewrote it as 2x. Now, I only pointed that out because now we can go ahead and compare them. It's being multiplied, which means it's a shrink or a stretch. It's inside the function, which means it's horizontal, and it's a whole number, which tells me that it's a horizontal shrink. Not the easiest to write with. I should have just used an H. Horizontal shrink. So we've already described it. Now all we have to do is go back and graph it. So what they've done, they made 2 tables just because, being that it's a more complex parent function, we just can't graph that right off the bat. So we made a table for the parent function, f of x, and then we also made a table for g of x, and then we just plugged numbers in. So they chose a few numbers. If you notice on this one, instead of just -2, on, they just went a little further. That doesn't matter. You'll learn that sometimes you can't find the vertex, the point where it switches and goes the other direction, so you have to continue on one way or the other in your table. You sometimes have to try both till you figure it out to see where it turns directions. So on f of x, they went a little further this way because if you notice, the vertex is right here because we finally get back to -2 and -2. So they had to go further this way to see some points on that line or that function. And that one, f of x is the blue. So they graphed it there. So then they made a table for g of x and they plugged in, if you notice, they plugged in like 0.5, 1.5. I hardly ever do that, and I probably wouldn't have. Okay. So I would have just plugged in -2, -1, 0, 1, because let's see, if we plug one of those in, well, -2 times 2 is -4, plus 2 is -2, but then you have absolute value of -2 is +2, minus 3 is -1. So that's all they've done is they've plugged these x values into this equation or function. So then -2, -1, -1, -3, 0, -1. See, I wouldn't have done the point in between, which is fine, to each his own, but you do not have to put decimals in there. And that's all we have to do on that one. We have to graph them and then describe it, and it was a horizontal shrink, and that was it. It's just these aren't as simple like absolute value of x anymore. So I am actually, rather than making you try this one on your own, I'm just going to do one of these with you. So I'm not going to make you do 5. We can cross it out. We're just going to do 6 together. So you're going to write this down as we go. If you want to go ahead and pause it just so you can write the problems down, that's fine. But I'm just going to do this one with you. Okay, on number 6, or this is number 6, right? Yes, we're only doing number 6. If you haven't already paused the video to at least write those down, do that, but I'm going to do this one with you. I'm not going to make you try it on your own. So they tell us to graph both of these functions, f of x and g of x, and then compare them. But I want to go ahead and compare them first. To me, I can go ahead and kind of figure it out, and then I just have to graph. So looking at this, the only difference is that when this one has an x, this one has a -4x. Other than that, they're exactly the same. Okay, so if we think about the only time we have to replace x with something else, so there's f of x, is when this one equals f of -4x. Because that would mean I go and anywhere there's an x in my original function, f of x, I would just write -4x instead. And that's all that has happened. That's all we did from one to the other, was where there was an x, we replaced it with -4x. Well, that's what this tells me to do. Okay, so now we know it's being multiplied, so we know it's either a vertical stretch or shrink or a horizontal stretch or shrink, and it's inside, so that tells me it's either a horizontal stretch or shrink, okay? And then it's a whole number. We have lots of checklists to go through. Okay, you can use your definitions for this from your notes. So when it's a whole number inside, that tells me it's a horizontal stretch, shrink. Sorry, horizontal shrink. I'm getting confused with the vertical one. Okay, so that is a horizontal shrink. We know that already from the problem. Okay, now let's graph them. Okay, so I have f of x equals x plus 2 plus 2. So let's plug in for f of x a table. Okay. -2 plus 2 is 0, plus 2 is 2. -1 plus 2 is 1, plus 2 is 3. 0 plus 2 is 2, plus 2 is 4. 3, 4, 5, 4, 5, 6. So I haven't found my vertex yet, so I'm going to extend my table. Let's see. -3 plus 2 is -1. 1 plus 2 is 3. So I had it right there. That'd be if I went my table further. Okay, so my vertex is at -2, 2. -2, 2. Then I have -3, 3. -1, 3. 0, 4, 1, 5. Okay, so we can see it goes like this. That's f of x. Okay, so then if I graph g of x, also has a negative in it, so it's probably going to flip. So let's see, I'm going to go ahead and start with -3 since I did over there. So -4 times -3 is +12, plus 2 is 14. Absolute value of that's 14, 15, 16. -2 times -4 is 8, plus 2 is 10, plus 2 is 12. That's 4, plus 2 is 6, 7, 8. I'm just plugging these into this function. 4 times 0 is 0, plus 2 is 2, plus that is 4. -4 plus 2 is -2. Absolute value of that is 2. 2 plus 2 is 4. Did I do that right? Hold on. 0 plus 2 is 2. Plus 2 is 4. If I plug in 1, -4 plus 2 is -2. Absolute value of that is 2 plus 2. So is it between there? Okay, so the video cut off. I don't know. It was kind of messing up, so I stopped it. So I'm not exactly sure where I left off, but I'm going to put this up. And if you look, this looks weird because we have 2 4s. It confused me for a second too. I forgot. So what happens is that means we know it's got to cross the y-axis at 4 because it's a horizontal one. Okay, but we have 2 that go to 4. We need a vertex in there, so I'm going to plug a number in between them. Well, it's 0 and 1, so I'm going to plug in 1/2 and see what I get for x. So if I plug 1/2 in up here for x, I have -4 times 1/2, so half of -4 is -2. -2 plus 2 is 0, plus 2 is 2. Thank goodness I didn't get 4 again. So that lets me know that's my vertex. Okay, so 1/2, 2. Then I have 0, 4, 1, 4, 2, all the way up to 12 somewhere, and is that right? Hold on. -4 times 2 is -8, plus 10 is -6. That's an 8. I don't know why I said 12. Okay. So 4, 5, 6, 7, 8. Sorry, guys. 2, 8. So this one goes up really small like that. So do you see why I wanted to do this one with you? It had a kink in it, okay? So that's why I didn't want you to try that one on your own. Sorry, I'll turn back so you can see the graph. It's like neat, but they cross the y-axis at the same place because it's a horizontal one. When it's vertical, they have the same vertex. When it's horizontal, they cross the y-axis at the same place. On example 4, now we've got let g of x equal -2 times x minus 1 plus 3. And then it says describe the transformations from the graph of f of x equals the absolute value of x. So this one is our parent function. And they're asking us just to describe everything that happens in this from this. Now, I do want to come back up and look for a second because I don't want y'all to get confused that up here, the reason it only was a horizontal shrink, was because this was the parent function. It already had all this going on in the original function. The only change was times this 2. down here on example 4, we have a lot going on in this because it started out just x. We have all this stuff being added. So we have several transformations happening. So they're asking us to describe them, then graph G. So break it down and do it individually, and there's not a right order. I don't want y'all to think that, oh, you have to look at the one being multiplied first and then adding. It doesn't matter because you're going to get them all. I just like to start with the one being multiplied. So on here, they didn't, but I'm going to. So we have times 2. So it's being multiplied, which tells me it's a stretch or a shrink. It's outside the function, which lets me know it's vertical, and it's a whole number, so it is a vertical stretch. So I would say a vertical stretch by 2. Okay, that's also a negative 2. That negative tells me there's a reflection. Okay, it's outside the function, which tells me it reflects across the x-axis. So I've done this one. We've got a stretch, a vertical stretch, a reflection across the x-axis. So I'm done with the negative, done with the 2. Okay, now I have a minus 1 inside the function. So a subtraction or addition is a translation. Okay, it's inside the function, which tells me it's horizontal. So it translated horizontally, or a horizontal translation, 1 unit right. For some reason, when it's minus, it's right. When it's plus, it's left. So 1 unit right. So there's that one. So mark it out. The only thing I have left is this plus 3. So again, it's adding or subtracting, which tells me it's a translation. It's outside the function this time, which lets me know it's vertical. So we have a vertical translation. It's plus 3, so 3 units up. A vertical translation, 3 units up. So that one had 4 different things that were happening to it. Okay, so now we just have to graph B. We don't even have to graph the parent function. You can, but you don't have to. So you can make a table, and we just plug in some numbers that we think into this equation. So they started with negative 1. So negative 1 minus 1 is negative 2. Absolute value of that is 2. 2 times negative 2 is negative 4. Negative 4 plus 3 is negative 1. So we're plugging in these values to get our points. And then we graph it. So negative 1, 0, 1, 1, 3, 2, 1, they said 3, negative 1. So it's this red one right here. That's what it would look like if we were to graph it. What they've done here is they've shown each individual here. The black one's the original after one transformation. So they said if you translated it horizontally 1 unit, so from the black, or no, that is the first one. They did that. Then the blue was where they stretched it vertically. Then green is where they reflected it. And then red is they translated it up 3 units. Sorry, I got an email. That's all that noise was. Okay, so now again, rather than you having to try this one on your own, I'm just going to do problem number 7 with you. So you can pause the video to get it written down, and then I'm just going to go over it with you. Okay, last problem. If you haven't already copied this down, go ahead and pause the video and do that. I'm going to do this one with you. Okay, so all I did was I went ahead and graphed f of x equals the absolute value of x. You don't have to do that till we actually graph. I just was getting it out of the way. So this is our new one. G of x equals the absolute value of negative 1/2 x plus 2, close absolute value, plus 1. And it says describe this transformation. So we have several things going on in here. So we're going to break it down piece by piece. I kind of work backwards. We're going to look at the things being multiplied or divided first, then we'll look at adding and subtracting. So we have times a negative 1/2 here. Okay, so since it's inside the function and it's a fraction, that is a horizontal stretch. Okay, it's also negative. That lets me know there's some reflection. Okay, since the negative is inside, that'd be across the y-axis. So I'm going to write that part down first. If you want to make a note of what you were talking about, we were talking about the negative 1/2 x. That is a horizontal stretch. And you can just say and reflection. You don't have to say across which one right now. Okay. Then I also have a plus 2 that's inside. Remember, if it's plus or minus, that's either a horizontal or vertical translation. Since it's inside, so I'm talking about the plus 2, that is a horizontal translation. And again, you can look back at your definitions to help you with this part. Okay, and then the last part, the plus 1 that's outside, since it's outside, that is a vertical translation. This is what it means by describe it. We're telling all the individual transformations. Okay, so now we can graph it. We're going to make a table with some data. So I have no clue where this comes out, so I'm going to start with -3 and hope that I cover it all. We may end up having to extend our table. Just depends on the problem. So I'm going to come over here. Let me grab my calculator just so I can double check myself. Okay, so if I plug in -3, I have -1/2 times -3, which is 1.5, so 3/2, plus 2, absolute value of that, and then plus 1, so that is 4.5. Okay, if I plug in -2, -1/2 times -2 cancels and is just 1. Plus 2 is 3. Absolute value of that is 3. Plus 1 is 4. Okay, if we plug in -1, -1 times -1/2 is just positive 1/2. Plus 2 is 2.5. Gosh, I had such a brain fart just then. Okay, plus 1 is 3.5. Okay, if I plug in 0, that cancels. Plus 2, absolute value of 2 is 2, plus 1 is 3. Okay, if I plug in 1, I get -1/2 plus 2 is 1.5. Then absolute value of that, so 2.5. I keep thinking it's going to turn around at some point, but we're going to end up probably having to extend our table. No big deal. The next number we're plugging in is 2. -1/2 times 2 is just -1. -1 plus 2 is 1. 1 plus 1 is 2. I feel like we should have already flipped it. I would have thought it would have been at -2. Maybe not. Okay, so 3. 3 times -1/2 is -1/2. Or excuse me, -1.5. Plus 2 is 0.5. So plus 1 is 1.5. Okay, I'm going to extend my table further that way and see. So if I plug in -4, -1/2 times 4 is -2, plus 2 is 0, plus 1 is 1. What? Is that what y'all get when you plug in -4? -4 times -1/2, negatives cancel, half of 4 is 2, 2 plus 2 is 4, plus 1 is 5. I don't know what I was doing. I knew that didn't sound right. Okay, I'm going to plug in -5. Sometimes you have to continue it until you find it. And then plus 2 is 4.5, plus 1 is 5.5. Still not finding it. Okay, I'm going to plug in 4. I'm going to go the other way. -1/2 times 4 would be -2. Plus 2 is 0. Plus 1 is 1. Maybe that's what I was plugging in. -1/2 times 5 is -2.5, plus 2 is -0.5, absolute value is 0.5, plus 1 is 1.5. Oh my goodness, we finally found it. So here's my vertex. Yay! That's what I meant by you don't really know what numbers to use. You just kind of have to figure out if you need to extend it. So now we can finally graph. So I'm going to graph my vertex first. It's at the point 4, 1. So 1, 2, 3, 4, up 1. Then I have 3 and 1.5. 2, 3, 1.5. I did those a little close. 4, 1.5, 2, and 2. So there's where it crosses our other one. 1 and 2.5. So it's very, very, I'm going to go back and do just the whole numbers, because the points in between are just in between it. So it's like, that one is another reason why I wanted to do it with you. It kind of seemed like it went on forever before we found the vertex. It's very open wide.